Solving inequalities is something you should be familiar with and easy to do, but sometimes we want to solve complicated functions, and we can solve these inequalities of those functions using the graph, so looking at different regions in the graph. So remember that when you solve inequalities, you don't get something like x equals to one specific value. You always get a range of values, x less than something, or x more than something, x less than or equal to, x more than or equal to. So we'll get a range of values that will satisfy our inequality. And in order to do that, we're going to look at the required regions in the graph. So we could have one region, two regions, three regions, and hopefully it's going to make sense. I'm going to go through four very different examples just to illustrate the different ways of solving these function inequalities, and they all follow the same method and same procedure throughout. So try to grasp the idea from the first example and then follow through with the others. For every example, I've already graphed the function just to pass time and to make it easier for us to see. And for every function, I've found the point of intersection already. So in an exam, by the time you reach to solving this question, you would have already graphed the functions. So what the graph tells you is I want you to solve 4x minus 1 is greater than 5. Now, ideally, you could do this using inequalities. You could solve it by hand. But if the question asks you to use the graph, then you have to. So we're going to use the graph. The green part is our function 4x minus 1, and the straight line is y equals to 5. So what you want to do is make sure that both sides of your function have been graphed already. So we've graphed, both sides of your inequality have been graphed, and they are. Now, what you're looking at now, which is the important part of this video, is understanding what this means. What this tells you is that, well, this is a function. Let's say this is f of x, and this is another function, let's say g of x. F of x is also another way of saying y value. And so this is another way of saying y value. So I want to know, when is the y value here of 4x minus 1, when is the answer bigger than the y value here, which is 5? So for every example, you need to look at the y-axis region. When is this graph bigger? When is the y value on this side of the graph bigger than 5? It's going to make sense the more examples we do, so don't worry. So this line, at the moment, these are the y values of this line, which are currently below 5. So all these coordinates, the 0.1, 0.2, 0.3, and 1, they have a y coordinate of 3, 2, 1, and so on. They're all below 5. When is the y value of this graph bigger than 5? And it immediately starts here. So these are the parts I'm looking at. So this is when my 4x minus 1 is bigger than y equals to 5. So you can think of it as an inequality, or you can just immediately look at the graph. When is this graph bigger than my other graph? And it precisely starts when x is equal to 1.5. So as soon as 1.5 starts, strictly bigger than 1.5, that's when my green graph is bigger than y equals to 5. So the answer is just simply when x is bigger than 1.5. So if you substitute any number strictly bigger than 1.5, so let's say 1.51 into this answer will be bigger than 5. And you can check it by actually solving the inequality. Now, it seems a bit ridiculous because you can actually just solve it on your own, and it seems quite easy to do here, but it gets a bit more complicated when you have different examples of graphs. So try to pay attention to the other ones. But you're basically looking at, when is this graph bigger than the other graph? And you need to pick out the x values that would satisfy this and test them out. So this is the first one. The second one is when we have two linear graphs. So we have the graphs done here, and I've also found the point of intersection because that's going to help us. This is my 3 minus 5x, and this is my 3x plus 1. This time the inequality is then less than or equal to, so when we do our final answer, we have to have x something or equal to. So just to note that you have to keep the consistency. Now, I want to know when is my green graph less than my the black one. So the green graph is less than the black one. So when I say less than, I'm talking about the y values, not the x values. It's less than the black line precisely from this point onwards. Because if I take any negative values here, even let's say 0.1, my green graph is higher. So the y value here is higher than my black graph. Let's look at one specific example. If I substitute 0 into my green function, so my 3 minus 5x, my y value is going to be 3. But if I substitute 0 into my 3x plus 1 function, my y value is 1. And so when x equals to 0, I'm going to get this will be 3 and this will be 1, which is not greater than. So 3 is not less than or equal to 1, 1 is not greater than or equal to 3. So any values from here onwards, any x values from here onwards do not satisfy this inequality. The only values that would give me a 3 minus 5x to be less than or equal to 3x plus 1 is when x is precisely starting at 0.25 and greater. So when I am here, x equals to 0.25, and anything bigger, my 3 minus 5x graph is less than the 3x plus 1 graph. So my answer is just when x is bigger than or equal to 0.25. Or you can write it as a fraction 1 over 4. You can always check your answer by solving the inequality. If you actually solve it, you're going to end up with the same answer. Let's say you have quadratics, and this is a common inequality question they would give you with quadratics. So they ask you, you have this quadratic x squared minus x minus 6, and when are the values, when is my function bigger than or equal to 0? So equal to 0 is my y equals to 0, which is also known as the x-axis. So I am looking at when is it bigger than or equal to 0. So again, let's highlight. So this is the x-axis that I'm looking at. And I want to know when is my green line above my other graph. So it's precisely here and here. And when does this happen? Remember, take the intersection of these two, which is basically the intersection of the x-axis, which is also the roots and the solution. So just a point, intersection with 0, with y equals 0, is the same as the roots, the zeros, the solutions of your quadratic. This precisely happens when x is bigger than, so notice we're looking at when the graph is going this way, so this way. So we're looking at when x is, less than or equal to -2, and we're looking at when x is bigger than or equal to 3. So we're looking at all these values. Because if I pick anything less than 2, I'm going to get the graph getting negative y values or below 0. So the graph is bigger than or equal to 0 when x is less than or equal to -2 and when x is bigger than or equal to 3. If the question, so this is an if you had the other way around, less than or equal to 0, then you're looking at this region. So you're looking at below the x-axis, and this happens when you have values between -2 and 3. So you're going to write x is between 3 and -2. So this is if you're going less than. So just try to see which region are you looking at and which values would satisfy. And if you're unsure, just check your values. Substitute in, say, a value less than -2, which is -3, and see if the answer here is going to give you something bigger than 0. And then substitute 4 into here and see that your answer is going to give you something bigger than 0. So it's really easy to check your answers with these type of questions. And then for the last one, we have an exponential and a quadratic. So this is where I said, well, it's not easy to solve them using inequalities, using normal algebraic inequality. So you'll have to use the graph. So I've graphed the two functions. This is my 2x, this is my quadratic. And I've pointed out the points of intersection already. And I want to know when is this is the green graph. Oops. I want to know when is the green graph bigger than my black graph. And in here, my green graph is underneath the quadratic. I'll just call them by their names. The exponential is below the quadratic, so it's not bigger than, it's less than. And in here, my exponential is above my quadratic line. So this is the area that I need. And also here, yes, the quadratic, the exponential is quite a low value, but it's still higher than the quadratic. So this is the area I'm looking at. And if you notice, let's say you have this as an x value, while your exponential will have this y value, which is a positive one, but your quadratic will have a negative value, which is less. So that's what you need. So the inequality is precisely satisfied when x is from here and down. So when you have x being less than or equal to, so we're taking the same inequality, so the equal to inequality, negative 1.93, or when x, we're looking at this x value and onwards, so this x value and onwards, it's when x is bigger than or equal to 1.26. So just be aware with the equal to or not equal to, if it's said strictly bigger than, then you have to stick with the strictly bigger than and less than. So you have to stick with the whether it says equal to or less to. I know some of you might ask, which one do we pick? Well, you just stick with the same format as the beginning. So just look at the region, highlight the regions that you want. It's easily spotted if you see which the graph that you want is higher or below the other graph, depending on the inequality, and make sure you pick out the intersection. So you have to pick the intersections first, and then look at the region you're pointing out at. If the question was when are they equal, then your answers are going to be just the intersection point. So, or x equals to 1.26. But because it's an inequality, then you have to go beyond the intersection, whether less or more. Because you're looking at, remember what I said in the beginning, you're looking at regions and not exact equal signs. Hopefully the video was clear, and try to read through the slides if you have any more doubts.